So now that we've had a chance to understand long division of polynomials, we're going to talk about synthetic division of polynomials, which is going to shorten that long drawn out process so much. So the first thing we need to know, and should be a review concept for us, but we have the factor theorem. And essentially what the factor theorem says is if we're given a polynomial and we evaluate it at c, right? So if we plug c into that polynomial and the output is 0, what that means is if c represents a 0, if c is a 0, then we know the factor, right? And the factor is always going to be the opposite. So if you think about, a quadratic function and we factored it and we pull the zeros out, those are the opposite numbers. So this just says, hey, if we know the 0, we can build the factor, okay? We have this remainder theorem, which essentially evaluating the function at some number c, right? If we plug c again into the function, that would be the same as the remainder if we divided by that factor x minus c. And we'll look at an example of that in a minute. And then also synthetic division. And synthetic division is sometimes called synthetic substitution, because really instead of, dividing and subtracting, we're going to be multiplying and adding, and it's just going to be like plugging the number into the function and getting a number back out. It's a pretty quick process, but we do have an important rule. We have to have a linear factor. We have to be able to pull that 0 c out of the factor, all right? So we're going to divide by the 0 that would come from the divisor. So for example here, if my divisor is x plus 2, then I'm going to use x equals negative 2 in my synthetic division. Okay? So let's do an example of synthetic division. So we're going to use synthetic division here to find the quotient and the remainder. So we still have a divisor and we still have a dividend. And you'll notice in my dividend I have a cubic term, a squared term, but I'm missing a linear term. So, and then I have my constant. But if I were to write my dividend, the way I'm going to need to do it is I'm going to need to plug a placeholder in. So this would be 2x cubed plus 7x squared plus 0x minus 5. And then the value I'm going to use for my synthetic division or synthetic substitution, I'm going to sub in x equals negative 3. Okay, so those are the two things. We need to make sure we use a placeholder and then we pull the opposite or the 0, the opposite value out of that linear factor. So I'm going to set this up with my negative 3 over here. And then I'm going to list my coefficients from my dividend, 2, 7, 0, and negative 5. And so this is very important why we use the placeholder, because if I do not have that 0 value there, I'm going to get my answer wrong. So you need to make sure everything is organized. Synthetic division, synthetic substitution, it's contingent on everything being in the right spot. So, I don't know why we just did that. So what we're going to do here is we're going to bring down the first number. We always bring that down first. So bring down the 2. And then we're going to multiply. We're going to multiply and put that number up here. So negative 3 times 2 gives me negative 6. After I multiply, I bring that value down. I get a new value. So I'm going to add here. 7 plus negative 6 is 1. So we'll repeat this 2 more times. negative 3 times 1 is negative 3. We'll add down again. 0 minus 3 is minus 3. And we'll do this one last time. Pull that through here. Okay, so negative 3 times negative 3 gives us 9. Adding down again, my last value is 4. So I'm just going to redo that one more time here. I'm going to set this up and work through the problem again without all of the arrows. So I put my negative 3. I list my coefficients, 2, 7, 0, negative 5. We bring down the first value, 2. I multiply. Negative 3 times 2 is negative 6. I add positive 1. Negative 3 times that 1 is negative 3. I add and I get negative 3. Negative 3 times negative 3 is 9. I add down and get 4. Okay, so that's how the synthetic division works. And now that we have this jumble, we need to know how to interpret it. So these numbers represent coefficients of my quotient. And they are going to be 1 degree less than my original dividend, p of x. So we're going to be taking that, and we started with x cubed, so these represent a quadratic. So I have that my quotient, q of x, is 2x squared plus 1x minus 3, and that would be like saying x to the 0, but we don't need that. And we don't need the 1 in front of the x here. Okay? So that's my quotient. And I started with x squared because I originally had x cubed. The last piece we have here is the remainder. The remainder is going to come from what's left in the box. And in this case, my remainder, r of x, equals 4. So now we know how to identify a quotient and how to identify a remainder. And we're going to use this here. Consider our remainder theorem for the above dividend. And so the dividend that we started with in this problem was p of x equals 2x cubed plus 7x squared minus 5. So p of negative 3 equals 2 times negative 3 cubed plus 7 times negative 3 squared minus 5. If I plug negative 3 into my function, what value do I get when I simplify it? Plugging in negative 3, if I simplify this expression I have here on the right, I end up with 4. So that's what the remainder theorem, that's the connection there. And that's why we call this synthetic substitution as opposed to synthetic division sometimes. Because essentially I plugged in negative 3, I got out 4, and I used those other coefficients to create a quotient. So let's do another example here. I have x cubed minus 3x squared minus 13x plus 15, and we want to divide that by x minus 1. So we're going to do this division. And when we're done, we're going to write our answer in this special form such that p equals d times q plus r. So, we don't have to do our long division process here. when I set this up, I'm going to use x equals positive 1. And I'm choosing that positive 1 because that would be the number that would come out of my divisor factor as a 0. So because it's x minus 1, I use x equals positive 1. And then I'm going to list the coefficients of my dividend through here. So I have 1, -3, -13, and 15. And we did not have to use a placeholder because going from left to right, we have x cubed, x squared, x to the first, and x to the 0. Cubic, quadratic, linear, and then constant. 3, 2, 1, 0. So we have a term for every place in descending order. But of course, if one of those pieces had been missing, then we would have to write in there plus 0 for that linear term. But that's not the situation. Okay? So we set this up. We run through our process. 1 times 1 is 1. -3 plus 1 is -2. 1 times -2 is -2. Add down -15. 1 times -15 is -15. And we end up with a special number that makes us happy here, 0. So identifying our quotient, remember the quotient is 1 degree less than our original dividend that we were dividing by. So we started with x cubed. That means my quotient, q of x, is 1x squared minus 2x to the first minus 15x to the 0. Because we started with 3, so I wrote these numbers 1, 2, -2, and -15 with x squared, x to the first, x to the 0. And of course, we don't need that 1, we don't need this one, and we don't need x to the 0, so I'll just rewrite that here. This quotient is x squared minus 2x minus 15. And my remainder here is 0. So if I want to write my answer in that form, we're going to start with p of x. P of x equals x cubed minus 3x squared minus 13x plus 15. And what we can say now is that p of x is equal to my divisor, x minus 1, times my quotient, x squared minus 2x minus 15, plus my remainder. So my remainder here is 0. Do I really need to write that remainder? No, writing plus 0 doesn't change the problem at all. So here I have factored this, right? I've written it in the correct form, and now I have p written as a product of two factors. The first factor, x minus 1, we call that linear. The second factor, x squared minus 2x minus 15, is quadratic. Okay, so that's all we need to answer the question, but I want to extend our thought process here. So we could say write p of x as a product of linear factors. So p of x equals x minus 1 is already linear. Can I factor my quadratic part there, the part in green, which was originally my quotient? The answer is yes. X minus 5 and x plus 3. So now I've taken this and I've written it as a product of linear factors. And if I asked you to tell me the zeros now, That should be pretty easy for you because you'd say that x equals +1, +5, and -3. So we know the zeros of our function. We know that it was a cubic function rising from left to right if we consider our leading term test for end behavior. So I know my y-intercept is +15, 0, 15. So if I were to graph this, and I'm not pulled this up on my calculator, I know I have a 0 at -3 and at +5 and 1. So -3, 1, +5. We just said the end behavior is rising from left to right. We know the y-intercept is somewhere at +15, somewhere on the y-axis here. And I'll address that when I'm drawing it. So I'm going to draw from left to right. And then the last thing we think about is multiplicity. So each of these factors has an exponent of +1. And +1 as an exponent means we're going to cross. That's an odd multiplicity. So I'm going to cross at +3. I'm going to turn around, cross at 1, and then turn around and cross at +5. And we can just label this here 0, +15. So we have a good idea of what our graph looks like. And then again, this max and min, these high and low values, are extreme values here. We can't determine those without using our calculator until we get to our next math class, which is calculus.